It's a pleasure to introduce Sanjay Shakkottai. You may not know him. He is a professor in what department are you in?
It's Sunday, electrical and computer.
Yes. How many years have you been here?
Longer than you.
Is that true? When did you start?
2002.
Oh, yes. Here. We're excited about this stuff. Why? No, I'm just kidding. Because Google is rolling. Did they roll it out last week or the week? These products are being rolled out in the Google Pixel Book and the Pixel phone. So it's having incredible impact. So congratulations to you, and I'm excited to hear about it.
Thank you. So thanks, Adam, and thanks all for coming. I'm going to be talking about training-free approaches for essentially image inversion, editing, using sort of diffusion models and flow models. This is joint work. The lead on all this work is Litu. He's somewhere sitting here, hopefully. Yes, there he is. Litu's, but also with many other collaborators. Yuzua and Vincent Chu are with the Pixel team at Google. Nathaniel is with Imagine. So this, and they're sort of responsible for their big generative models. Abhishek was when he was at Google, he collaborated. He was at DeepMind. Now he's with Amazon's AGI. Constantine, of course, here with me. So I want to talk about training-free approaches for image editing, inversion, and so on. So there are, what does training-free mean is one question. What are diffusion and flow models, another thing, and what do I mean by image inversion editing? There are sort of different pieces which are not maybe fully clear what these words mean. I want to start with the canonical editing type problem. So the classic problem for these kinds of things is the inverse problem. So I've got an image, I've got some imaging system, and there's noise after that, and you're going to get measurements, which is some corrupted version of this ground truth image. Here is some A of X0 plus some noise. And this classic inverse problem is, given this image, you want to reconstruct the ground truth. This problem in general is ill-posed because there's, depending on how corrupted these measurements may be, there are infinitely many solutions that could satisfy sort of images. So one way to sort of deal with this problem is saying that, well, suppose I have some generative model or some model which has some understanding of how the data distribution over images look like, what images look like. So that's called a prior. Then you can use that somehow to ground this and sample an image which is consistent with sort of what images should look like. Okay? So this is sort of a generative or sampling approach to actually solving these kinds of inverse problems. Now, of course, there are many other ways of trying to solve these types of problems. I'm not going to do a broad history of these things. I'm just going to focus on sort of diffusion models based ways of solving this style of problem. But beyond that, that was just sort of noisy measurements. More generally, you could say the measurements is that I've got this image, somebody deleted parts of it, and I want to reconstruct this. That's one type of problem. That's an inverse problem. Or I give you a blurry image, I want to get a higher resolution version. Again, same thing. Stylistically, I've got some measurements, and I want to generate what I think the truth is, or different types of noise. But even beyond that, you can sort of say what really constitutes a measurement. It could be that I give you this image of this, this rose in this melting gold style, and say, generate a guitar with this style. I can think of this as the measurement, quote unquote, of a guitar, and I want to generate this. Okay? So this goes beyond sort of what you think of inverse problem, but essentially the same kind of thing. Okay? This is my measurements, quote unquote, on information, and this is my output. Or even beyond that, you could start thinking about content style composition, which is that I say that I want to generate an image. This is my style, this melting gold. This is my content, this particular dog with these floppy ears and this kind of a nose and so on. And now I want to generate an image which is consistent with these measurements. And so this is what we want to generate. By the way, the images I've shown you here are all from, the outputs are all from various tools I'm going to talk about in the today. Okay? So I want to talk about, so these various problems have different names. The first one is sort of inverse problems. The second is called generalized inverse problems. There's stylization, there's content style composition, but philosophically, they're all the same kinds of problems. And we want to sort of think about all of them. So to generate these, what we are going to use are diffusion models as a prior. So diffusion models have recently emerged as sort of the powerful foundation model for images, and essentially provides a pipeline for solving these kinds of inverse problems and composition problems. Okay, so so before I get into exactly what a diffusion model is and how you solve these kinds of problems, let's talk about the evolution of sort of the scale of these diffusion models. At its core, it's a black box which generates images. Okay, it samples over the distribution of quote unquote natural images. Presumably, this being trained with internet scale or data. So extremely large amounts of data are being used to train these models so that they provide a diverse collection of natural images according to image distribution. Okay, so in terms of when I get into the sort of types of the diffusion models for images, you'll see that the history goes back to 2015. So I'm just going to talk about some recent models which are out in the public. First sort of private model, but nevertheless something which is very popular was OpenAI's DALL-E model, which was a 12 billion parameter model. It's a pixel space model. So what does it mean? An image, you can think of a 512 cross 512 image as essentially you can just vectorize it in 3 colors, in which case it's 512 times 512 times 3, which is about 800,000 dimensions. So that you can just think of an image as a vector in 800,000 dimensions with some specific structure associated with it. So the first model was in pixel space, and the model was about 12B parameters. Very soon, latent space models became popular because potentially clearly not all vectors in 800,000 dimensional images. You should be able to sort of project it down to a much lower dimension. And stable diffusions, latent space was about 12,000 dimensions. And so there's an autoencoder that goes down to that lower dimension. All the generation happens in that, and then you lift it back. So this was a 1 billion parameter model. It's an open latent space model. And so that means the weights are known to, weights are available openly. And then so other researchers could actually start building on this. Around that time, Google's Imagine, it was again, it's a pixel space internal model. We don't know the size, at least not publicly known. So the publicly known ones are the Stability AI's pipeline, as well as the most recent one, Flux. These foundation models scaled up with the stable cascade being about 4 billion parameters. And in about 2024, mid summer of 24, the model sort of changed. These were what we think of as diffusion models. Something called flow models became popular, and they became the state of the art for image generation. These are Flux or Stability SD 3.5. So we'll talk about what the relation between diffusion and flow models in about 20 minutes or 30 minutes. So now at least the size of these models, it gives you some grounding. Okay. So so over the last few years with collaborators, we have been sort of thinking about solving inverse problems using some model along this line as the foundation model to help solve these problems. So in particular, PSLD we developed within UT with Alex's group, Constantine, Neetu led the charge with several other students. I'm going to talk about the details in a second. It was the first algorithm for solving inverse problems in latent space of diffusion models. This algorithm, however, had several approximations which were problematic. And so we collaborated with, again, the Pixel team. This is where we started collaborating with the Pixel team to sort of to help reduce the bias. And I'm going to talk about the details. This all as background. That's really not the focus of this today's talk. Then what I want to talk about is sort of very recent work, which is beyond these algorithms. If you want to do stylization, editing, for diffusion models. So the state of the art is something we recently developed. This is going to be published in IPA this time, and this is joined with the Pixel and Imagine team. I'll talk about the details in a second. And then the next is that how do you deal with flow algorithms? How do you solve these kinds of problems with flow algorithms? And that's going to be the last part of my talk. So really, I'm going to talk a little bit of this, mostly that, but I'll give you the history of this. That's the sort of outline of today's talk. So what is a diffusion model? First, let's start very quickly. A diffusion model does the following. It starts from noise, denoises the noise a little bit iteratively, and tries to get to an image. So this is the usual story, and this is this image is taken from Song et al.'s a clear paper. And the way they explain it is that you start from an image, see, add a little bit of noise, more and more noise till you get pure noise, and try to predict what's the amount of noise you are adding so that you could denoise it and get things. But what's mathematically really going on is the following. Think of a vector xt, which is, let's just think about it in pixel space. It's a vector about 800,000 dimensions. You sample a vector, a pure Gaussian. Okay, so you have a density function, which is that of a Gaussian. And you want to develop a Markov process, which means a continuous state space, continuous time process, whose density evolves. And at terminal state, it is the density of the image distribution. So that's what you want. You are looking for a density evolution. Okay. You start from the density of a Gaussian, evolving, and that density ends up with quote unquote image density. So what is needed to do that? Well, it's a continuous time, continuous state space. So you have this stochastic differential equation, which encodes this Markov process. What does it do? TXT. That means in a small amount of time, how much will your state change? So I start with a random vector x0 or x capital T. Let's say moving backward in time. TXT means that there's a slight difference in time. How much will change happen? It consists of two parts. One is called the drift or the velocity field. The other is called the diffusion field. Let's look at this term. This box here, which I've pointed out with my hand, or maybe because people may be online, let's see. This part thinks it is essentially a vector field, which is pointing in some particular direction. And it says, take this vector and travel a distance multiplied by dt. So take a small step here in the direction of this vector. This is again 800,000 vector. So if I'm at this point, I'm going, and the vector points down, I'm going to go that. That's what this is saying. It's deterministically moving xt in a certain amount. But then you add a little bit of noise. This is Brownian motion, meaning over a small amount of time, it's a Gaussian vector of extremely small variance. So you take a step in some direction and just perturb it a little bit. That's your evolution. And there's something called the Fokker-Planck equation that says that if you've got a drift field and a diffusion, it tells you how the density evolves. And so the whole game is how do you design these quantities, the vector field, drift field, and the diffusion, such that starting from whatever you want as the initial condition, in this case, Gaussian, which is easy to sample, I want to end up with the image distribution. So that's really the formal mathematical question. And over the last 15 years, this has been, the theory for all this is classical, 50, 60 years old. But for the image domain, how do you learn these kinds of things? That has been worked out. And it turns out that the key thing is to learn what the drift should be, that's how the vector should point. And that depends on something called the score function. I'm not going to go into details of what exactly the score function is, but suffice to say that you can learn this from data. In particular, if I give you a large corpus of images, then what you can do is the following. For each image, create a noisy version of it, okay, and consider this paired data. If I have this paired data set, then they're essentially using regression, you can learn this score function. And so that's really what these diffusion models, all this stuff is pre-trained. This is not using inference. Okay? I create this whole data set, create these score functions. There's a function of time. This time translates to the amount of noise you add. So you have a number of score functions, at least conceptually. And then what you do is you start from pure noise, send it into a denoiser, which is this thing, evolve it, so on, and you finally get an image. There are lots of things about how you discretize it, how many steps, and all that stuff, but we'll skip those details. It's at least conceptually this pipeline of a diffusion model.
Sanjay, maybe you want to mention that people want to see those.
That's right. There's a mathematical tutorial on diffusion models, how the mathematics of this work. It's on the IFML website, so you can just see that on YouTube. And the history of this, in terms of the development of these generative models for images, it goes back to sort of a recent sort of important paper was Salt Dickinson et al. In 2015, which proposed this kind of a pipeline. At that point, the methods for image generation were something else. At that point, actually, autoencoders and then GANs were popular. This is when first diffusion models were proposed. By about 2019, Song and Armand actually showed the state-of-the-art models were diffusions. And then there are several other groups, including Song et al., Ho et al., and so on, developed a bunch of types of diffusion models, which has led to sort of the current way of thinking of it. Okay? Again, if you go to the notes, the detailed references are there, or if you can get hold of these slides, I'm happy to share it. Footnotes give you various references. All right. So far, I've just talked about generation. What this does is I've got a black box which evolves to give you samples of images. This talk, what I want to do is to solve problems such as infilling, denoising, stylization, and so on, which are all essentially examples of something called posterior sampling. What does it mean? Well, I give you some measurements Y, in this case, this particular image, or in this case, this triplet. And what I want is not to sample from the data distribution, which is just E0, but a conditional distribution. What I want to say, this in the stylization, I want to say, I don't want to generate any dog. I want to generate a dog condition that this happens. Okay? So this is just conditional. I want to sample from this conditional distribution. So naturally, I can go back to the diffusion model, and instead of sort of looking at sort of the unconditional score, you can do the conditional score and run this model and give you whatever you want. The problem is, of course, we don't have this unconditional score. You could try to train a new model for that, but that's not the point. Somebody has already spent a lot of effort and money building an unconditional score, so you'd like to use that. There are a couple of ways to do this. One is you can take this unconditional score to lower some sort of fine-tuning on it with limited amount of samples. Say you want melting golden style, get some images of that style, fine-tune it, and then run it. These are called training-based methods. I'm going to talk about training-free methods, which is a synonym for something called test time optimization in language models. Okay. What does that mean? It means that I want to just, during the inference time itself, I want to do something to actually solve this condition. So if you want to take that approach, let's look a little more closely at this quantity. It's basically inside this, outside the gradient and log, essentially it's sort of the density of how a noisy image would look if for a particular set of measurements. So let's look at the density function, right? Bayes rule. If I do Bayes rule, I can switch the measurements and the information. And if I take log, it becomes the sum of three terms. The first term is what is the density of measurements if I had given the noisy image. The second term is just the density of just the images itself, which is what the score function already gives me. And a third term. If I take a gradient, this term does not depend on x. So there are only two terms, and that's basically where we get. It says that if you want to do posterior sampling, there is this score function, which is basically a vector pointing in some direction. But that vector is pointing just generally towards the manifold of images. You want to tilt the vector a little bit at each time to be consistent with your measurements. So you add a correction term. Okay? This is which we don't know. And the question is, how can you approximate this during test time? So this is what we mean by training-free methods. So you want to approximate this while you're running the inference time. Okay, so now getting to this, PSLD was an algorithm that came up with an approximation which worked in latent space. It generalized sort of prior work called DPS, which was a pixel space diffusion algorithm. But since we needed to work in the latent space of a VAE, we needed to do something else to get the algorithm to work. This talk is not about what this algorithm is, but suffice some important takeaways will motivate why we are actually working on other problems as well. So the goal, if you recall, is to approximate this during inference time or during test time. Okay. So this is essentially an intuition of consistency, correcting the gradient to be consistent with the measurements. And what we can do is to come up with an approximation in test time, which is also in the diffusion world, it's called training free. The test time optimization is also called training free step. And to do this requires a gradient computation at each time you're running the denoiser with respect to the input of the score function. So if you could do that one gradient calculation at each time, and that will tell you how to correct your drift approximately and run this. So that's what this algorithm did. At that time, it was state of the art. I don't want to even show you these images. Let's continue through to see how this goes.
So the prior work which I knew, which I know of, right? So there you already had the mapping. So A from X,
All these, okay, very good.
right? But now you don't have a map.
For the style, we will come to style. For the prior work and for a while, what I'm going to talk about, I'm going to assume I have a mapping. I have got a neural network, which is a measurement system. When you talk about style, things change. But let's just think about sort of inverse problems for now, where I know the forward object. Okay? Or I have a neural network that approximates the forward object.
So you know the mapping from X.
Exactly.
But where did you need to use that in the previous slide?
That later,
If you look into this,
I think really said this.
when you're taking the gradient, you need to take the gradient backdrop through all that stuff. And which also through the score network you access to. I don't want, because this is not what I want to talk about at all. I'm giving you the background to even say, why are we working on the problems we are working on now? This is a separate talk. Again, another talk in IFML. It's a different video. You can actually see the details of this problem. Okay, the problem is, first, even if you put backdrop, I said that's an approximate solution. We realize that the approximation is essentially just a Taylor's first order correction, and it's a really bad approximation theoretically. Okay. So the next thing you would try is a second order correction to this term, which means you have to have a Hessian. If you're doing a Taylor's correction, there's a second order term, which is a Hessian. These are gigantic matrices and computationally impossible. So what we came up with is essentially, instead of sort of actually trying to estimate Hessians, we came up with a way to just deal with traces of Hessians, which are sort of scalar quantities, and estimate this using some stochastic approximation in the loop algorithm. Again, all this is gobbledygook. If you haven't seen this before, it is some method which corrects the first one. That's really the takeaway. But the problem again here is that you still need to take you need to backdrop to the score network. And why is that a problem? We'll see that in a second. The second algorithm was much better than the first one, required much fewer steps of diffusion and gave higher quality results. Okay? So this was the first potential thing that we could do on a pixel kind. This was the pixel team, and this was something we could potentially do with that on a platform. You'll see that it's difficult to do that, and we'll see that in a few minutes why. All right. So this brings you to sort of prior stuff, and now I want to start talking about two algorithms, RB-Modulation and RF-Inversion, which are currently state of the art for diffusion models and flow models. So what is RB-Modulation? RB-Modulation is an algorithm for style, similar to what we have talked about, for stylization and editing, like test time optimization, but using a proximal method. What do I mean by that? I don't want now to take a gradient through this core network. And you'll see why in just in the next slide. So as before, it's a training-free approach. Every one of the previous algorithms requires this back propagation, and it's extremely expensive. So as an example of what I mean by context style composition, here's a problem. This is a pure stylization problem. I give you this mosaic kettle and ask you to generate a skyscraper in that style. So this is what you get. That's called a stylization problem. A content style composition means I give you two images, one of this and one of content, and ask you to generate something in this content with that style. And this is an example of it. Okay? So RB-Modulation is a tool that can do these kinds of things. And this pipeline is being productionized right now in certain Google pipelines. Okay. Why do we want to do any of these things? Okay. So these numbers are rough for a A100, roughly. If you want to do training time optimization, so I can try to fine tune my network itself for a particular style. There are a bunch of algorithms, several of them out of Google, but also various other well-known groups. Roughly, you need about tens of samples to actually fine tune that network. If you try to fine tune with just one sample and put a lot of weight on that, you can sort of lose core features. So it can lead to some very bad failure. So you need an order of 10 samples. In this case, when you're fine tuning, your gradients are computed with respect to the weights of the base model. It takes about 20 minutes per style if you're doing sort of LoRa style fine tuning, whereas full fine tuning takes hours. Okay? I'm talking about on one A1. That's just to give you some sense of the number. If you do test time optimization, Okay, then what you're doing is no longer gradients with respect to weights of the model. You're taking gradients with respect to the input to this core network. Okay? And one single sample suffices. That's basic because that's your example you have, that one measurement. However, it takes for a 1 billion size model, PSLD takes about 10 minutes to actually generate an image. So this includes multiple steps. Remember, you're not just doing one step. You do this, you move somewhere, you do this again, and so on. If you put all that together, it's about 10 minutes per image. Okay? And if you, by the time you get the Flux style model, these things are super hard to actually get anything in real time. So this sort of brings us to why RB modulation is so useful, because with the 4D size model, you can do it in about 40 seconds. You can generate an image. So that's really so because it's not it doesn't require a gradient through this core network. It is about 10,000 dimensions.
So, like, like in AD, like auto differentiation, there is forward process and backward process. Forward process, you can take a differential.
Oh, you can. I'm not saying not impossible. It is. You can actually do that. People, in fact, that's what we do in PSLD. Okay, you do that. It just takes 10 minutes on A100. That's all. It's a time taker. We are not saying there's no impossibility of anything here. Okay? You're willing to actually compute that gradient, yeah. But I want to do this fast without doing it. That's really the goal. Yeah. All right. So so for RB modulation, I'll be brief because I want to spend more of my time on flow models and RF models because that's really the state of the art today. So here I'll give you a sketch of what the idea is. So RB modulation is it's called reference-based modulation. It basically does two things. There's something called, let's go here. Recall what we had. We used Bayes' rule and said that you can decompose the drift into two parts. One which was the base score, which is the unconditional score, and the correction term, which was this consistency in respect to measurements. Now you can ask, instead of trying to compute this, you can just think of an optimal control problem. Say, suppose I put in a function u of t. I'd like to, whatever that function is. Can I find a u of t which is cheap, the path? So this is a low energy path, mean square path. Such that, so meanwhile, find such a path such that some terminal constraints are satisfied. What is this? So this is a path constraint plus some terminal constraint. The terminal constraint would say, hey, after you run this thing, you're going to end up in some state. This is hopefully the correct image. This is your measurement y. Okay. And this terminal constraint penalizes how much these things are far away from each other. Can you develop a controller? Think of this as just an optimal control problem.
Sorry, you want grad log PT of y fusion next. So y is the terminal should involve y and that's t. Y is involved. What's that?
So I've rescaled time from 0 to 1. I started time 0. I've switched time around here. Okay, I started time 0.
Time 1 is noise.
Time 1 is image. Time 0 is noise. So because I switched time around here for this particular file. I shouldn't have done that, but I did. So I start from noise, get to image. This is my image. I have some way of measuring how whether my image satisfies my constraint, my measurements. Okay, and that is my terminal constraint. I want to make this as close to 0 as possible. And while doing that, I want the energy of this one to be as small as possible. So I don't even have a noisy image. I have y. Okay. So how is this implemented? I'll map it back to this stylization problem in a second. Okay. Suppose I have a style extractor network, for example, CSD, such a style extractor network. Okay. Then you can use the terminal. That style extraction network becomes the terminal constraint. I'll use the style extractor network, put in whatever my style image, the golden rose image here, or with the melting gold image here. And on this side is whatever image I generate. Okay, so this is now my terminal constraint that the styles of these two should be close. So again, just like your measurement system, the question you ask, here again we have access to this kind of it, okay, such a style extractor. So once you have that, then you can formulate this problem. I'm not going to talk about how to solve this control problem. So what RB modulation does is essentially doesn't directly approximate that function like in previous methods. We actually formulate an optimal control problem, solve that, and that's a classic optimal control problem. If you knew the distribution, you can solve this. We don't know it, and we don't know the solution for general data distributions, but you can build an optimization to solve that. Then we can build a prox algorithm to solve that, and that's much faster than taking a backprop to the gradient. That's one piece of it. The other piece of it is some attention engineering, which I don't want to go into, which essentially disentangles content and side. Yes.
So currently, perhaps some said that here is an image, and it will tell you whether it's mosaic or not.
Yeah.
So
It'll give some code.
Yeah, it'll give you some score, which is like, is this mosaic? Is this image mosaic? Yes or no? And it'll give you some score.
Yes.
And you just need that score. You don't need an actual map. You don't need the actual.
Exactly. I need that neural network. So we use that neural network, and you can backprop through that score to actually push your guidance, intuitive. And that's what this controller is. It's not G. Sorry?
Yeah,
that neural network is G. Exactly. Okay. And this, so there are, so in terms of sort of an appellation study on this is what I think this is useful to see. So suppose I give you this particular style image. Okay. I give this as a label, a cat. Okay. If you just use the base model, this is what you're going to get. Let's ignore this. If we did some attention engineering to try to solve this problem, and if we use that alone, get this image. If you use just the optimal controller, you get this image. So it turns out that you need various things to actually work together to actually get what you want. Okay. So this is that I don't want to talk about this part because I have to go into sort of the architecture, but this pipeline was actually generating not just these images, but many, many more in production. And so this pipeline is actually being productionized. We can. I don't want to because I want to get to something else. So I can chat with you offline about that. Okay. So here are sort of several other examples of these kinds of things. I can give you a particular style, a particular content, and try to generate things. So and these are all sort of 40 seconds in the time scale for generating this on a 100 level thing. There's also another interesting thing which sort of training-based methods cannot directly do, which is generate novel styles. Suppose you say, I give you this image, and I give you this image, and say, imagine if I mix these two styles together. Okay, so I give you two styles as endpoints. Okay, and I want to generate a tiger in that mixed style. So now, once you have seen the terminal constraint, you can put various terminal constraints and interpolate between them. And depending on how you weight terminal constraint, you can sort of move along this whole axis. Okay? So you can generate novel styles which are not seen before, which is also a very useful thing for certain applications Google is thinking about. The other thing is images in the wild. So these are actually pictures somebody hand drew, and we can now ask, hey, here's this style, can you generate a house in this style? And it's able to be once, this is just a single image example. We're able to do these kinds of things. So the current status of this is that it's, I don't want to go too specifically into details, but various pipelines, including Pixel, Chromebook, tablet, and YouTube, are productionizing this. On an unrecorded channel, I can say something more, but on this, I just leave it at that. Okay. And so a lot of in the community also in Hugging Face, this demo was super popular. Okay, so I have about 15 minutes left, and I think let me now sort of switch from diffusion models to flow models. Okay, so in this part so far, even for RB modulation, I didn't really tell you what the algorithms were. I just gave you an idea. So for flow models, I want to go a little more detailed and actually talk about one algorithm, the RF algorithm, more carefully. Okay, so what is RF-Inversion? It's called Rectified Flow inversion. It is the first algorithm for inversion and editing with rectified flows. It's going to appear at ICLR this time. So, and rectified flow models I'll talk about that in a minute and talk about the history of that in a second. Then currently the state of the art for image generation. These are Flux and Stable Diffusion 3.5. Something very interesting about RF-Inversion is that you're doing test time inference without any test time optimization, not even approximate. And we'll see why this works. And because of that, the computation is lightweight enough that you can actually implement directly on an edge device without actually sending any data off the edge device. Okay? You just can work on the edge itself. And so you can imagine why this might be productionized and where it could be productionized. And so we'll just leave it at that. Here's an example of the kind of things we can do with RF-Inversion. I give you this reference image of this cat and give you the label silver cat sculpture. You should be able to generate this. Now, with that reference image, I give you a lion, you want to generate this, and so on. These are the kinds of things which you can do with RF-Inversion. And so, before we get into RF-Inversion, I want to first quickly talk about rectified flows. So rectified flows are an ODE model for generation of images. So it says, let's start from a noise sample and simply run an ordinary differential equation. So XT again is in pixel space is still that same giant vector. V is some velocity field, which is like whatever the vector drift field we saw, but it's just finally a gradient direction. So you're just running an ODE. You start from this noise, run it. If time is normalized from 0 to 1, you go from one point, you end up, and so you're moving samples from one distribution to some other distribution. And this can be trained, presumably, to move from whatever your training one side distribution was, the other side, it should be the distribution of names. So rectified flows there are several groups which sort of did it around the same time. One is, of course, Chang's at UT, Chang Liu and his group developed this. This was in ITL 2022. Lippmann's group had it also in 2022. Albergo and Van den Eyden had the sort of stochastic interpolants, which are similar kind of ideas, again, in the same time. So there are few groups which are responsible for this, and this was sort of the method. And Flux, which I talked about here, came out in 2024 and was a rectified flow-based model, which was the most which was the state-of-the-art model for image generation. So so roughly the reason Flux is these rectified flow models are better than diffusion models is that the path that it takes are sort of straighter, and if it's straighter, that means coarser discretization is enough. Finally you have to run all these in discrete. The straighter the path, I can take bigger steps, so you can actually lead to faster sampling. There's another advantage of the noise distribution being more general, but we are not going to use that property. This is really why Flux, these kinds of models are state of the art. So what is RF-Inversion then? Okay, so first, inversion essentially means the following. Suppose I start with an image, then can I go back to a noise? Okay, that's the inversion. The generation problem is start from noise and go to an image. Okay? That's what Flux. That's what any of these flow models give you. It gives you the vector field. Again, it's like a score network. It's some other network. It's a vector field. You feed in something, it will tell you where to go to the next step. But because it's a deterministic thing, I can always run it backwards, right? Meaning, if I could go slightly forward, I can say it's locally continuous, figure out what the direction forward is, instead just go back one little bit of step in that direction. If I discretize fine enough, then I can run that model either forward or backward. Okay? So there's one field that goes, this is the field that's given to you, but this is the field which can be approximated from the same model. Okay. So what inversion could potentially do is the following. Okay? I'm not saying that this is the inversion with the rectified flow field, but what you could potentially do is take a cat image, invert it all the way back to noise. Presumably this particular noise sample encodes something about this cat. And then in the flow model, you do different text conditioning, which will change the path somewhat, and then that may end up to a tiger. This is the hope. I haven't told you how to do this. So you do an inversion to go back to noise, and then you do a text conditioning and go forward back to your image. So then this pipeline, if it works, has no optimization. I run one flow backwards, I run one flow forward. Okay? If I just do this with RF, it is not going to work. we'll see what you need to do in a second. But yeah, you could also do these other kinds of things. I could take some corrupted thing, okay? And then run this backwards, do something here, and then condition on bedroom and go back here. Okay? So again, you're essentially doing some flow editing and noise editing to go between image space and noise space. So this is really the RF inversion pipeline. Okay. So I have about 10 minutes. Okay. In terms of when RF inversion, when we came up with RF inversion, there was no other algorithm to directly invert and edit using rectified flows. There are several approaches for diffusion models, including DDM inversion and so on. These are very good, but they do lead to inconsistencies in preservation of sort of structure conditioning. So one explanation is due to highly nonlinear paths, but after I finish this talk, you realize there's actually a deeper issue. Something called noise abduction isn't happening. Okay, I'll explain what noise abduction means in about 5 minutes, and then we'll see what the difference between these kinds of approaches and what we are doing. So, and other methods which maintain consistency, which are known, including our own method, are RB-Modulation, requires test time optimization, which even with the prox method is pretty expensive. Okay, so this is just summary that what we want is to get this inversion editing pipeline using rectified flows without doing any of these things, training, optimization, attention processing, or insert. Flow back and flow forward. Okay, so I told you roughly what a rectified, I told you graphically what a rectified flow is. So it is just a vector field, a velocity field. Okay? You start from at time 0, you start from noise, you run it, you get an image. And if you want to go backwards, it's very easy, the relation between the forward and the reverse. You just flip the sign of the velocity vector field you have, and then change time to 1 minus t, and that's all there is to it. It is very, very easy to go back and forth in these kinds of things. Once you've learned a forward model, you can approximate a backward model rather easy. Okay, so let's come to RF inversion. So I talked about sort of the images and noise. And there is, but really what you want to think about are, there's really typical images, which are what we think of nice image. There's no mathematical definition of this. This is a mental model I'm talking about. There's atypical images, things that look almost like images, but are clearly corrupted. And similarly, if in the Gaussian world, there's typical noise, what you get close to, if you sample a Gaussian, what noise would typically look like, and atypical noise, which is sort of because theoretically a Gaussian sample can be anything in RD. Okay? We can think of something called atypical. Again, I'm not defining any of this, but what your mental model with RF should be is the following. If you take typical data and flow back, presumably it'll give back typical noise because it's in the usual domain of the field which the flow model that you have learned, okay, the vector field you have learned. If you take an atypical sample, it's going to go not to a typical noise, but something else. Okay? This point is not an image, but somehow encodes some information about this character thing. Okay, so we could do one more thing. You can say, okay, that's what RF is doing. That's what the rectified flow drift field is doing. We'll do something else. We'll take every single image, couple it to a typical Gaussian noise sample, meaning for this one, RF might go here. Instead, I'll just couple it to something which is more typical, like a typical Gaussian sample, and try to find a low energy path, which can be solved using the minimum principle, okay, and move from this to this. So you can construct a second velocity field we'll call the controller field. Okay. So right now we have two fields. This both in the direction of image to noise. Okay. One which is one which is by just inverting the standard flux model, and the other is this particular field. So then, for this particular image, then there is one flow which is leading to a typical thing, another which is leading to a typical thing. So I want to interpolate between these two so that I can move this towards this point, so that it is an image and yet captures some structure of this. If I move that way, then I can start from this point and run a different forward controller. This forward controller will be grounded in this image, but will then But with the text conditioning, we hopefully come back here. So that's really what RF-Inversion is. It's an interpolation of two fields, a control field, which is grounding it on the noise structure of this image, and the second field, which is actually the rectified flows coupling. I'll give you a different way to explain this in a second, because this is this is not very clear. Yeah, sorry. Very good. I'm going to show you all that now. I want to look at this. So this is sort of a flow viewpoint of it. But actually, there's something more fundamental, I think, that is going on here, which is, I think this is the first counterfactual samplers for images. So what do I mean by a counterfactual sampler? So let me ask you this following question. Imagine if this cat were a silver sculpture. Or if you go to Pearl's stuff, so this is going to be based on Pearl's counterfactual theory. I know Adam is shaking his head, but it is, imagine if I did not smoke for the last 10 years. I don't smoke, but so imagine I did not smoke for the last 10 years, or I did smoke for the last 10 years. How would I look today? So what is Pearl's sort of structural causal model and reasoning? Suppose you have the following worldview. Again, this is a model. The model is the following. There's exogenous noise, Gaussian noise, which is out there. And there are observable random variables, x1 through xn. x1 depends on noise u1. x2 depends on x1 and noise u1 and u2, and so on. There's some causal model that takes the real thing that is driving things is the noise outside. But what is observable is a set of random variables x1 through xn, which is a directed acyclic graph. And therefore it's a joint distribution. What Pearl says for something called counterfactual reasoning is the following. If you have a structural causal model and an event, what you want to first do is something called noise abduction. You want to take your event and go back to the noise that might have generated this event. Okay? And second step is, once you have the noise, take an action, which is, in these words, a do calculus. Does that mean take the structural equations that generated this word and do surgery on it? Change any of these equations. Okay? That's a do. I'm changing one of the functions in the set of relations. And then do prediction. Send that noise through this new model and get a new sample. Okay? So this is his three-step reasoning. This is from the Pang and colleagues had this very nice tutorial, but this is essentially what counterfactual reasoning is about, this three-step process. Essentially, by the way, this is just a theoretical model. So it's not even, I'm saying that this is a unique model or something. What you really need to do is essentially find a way to find a noise sample and a flow field to go forward and backward that are consistent with each other, and where you can do this kind of surgery. Okay? That's really what RF-Inversion is doing. It is actually a prototype of such a counterfactual sample. Going back to noise through controlled inversion is a noise abduction. They're moving between those, interpolating between the point. Doing text conditioning is exactly the action, and generating through reverse control flow is a prediction. And I'll come back to Peter's question. Here are some examples. I think that, so suppose I start with just a reference image of a bank. I don't know what, this is from the wild. I don't know what the label that generated is. I start from this. So now let me just take the RF flow, run it back and run it forward and see what I get. So I take the reference image, run the rectified flow back to noise, and run it forward. No controller is what we get. Okay? Because it's not grounded on, there's no discretization error and noise that this thing drifts away from this image, that noise, and you flow it back forward, you're going to get something else. What a controller is doing is essentially giving negative feedback back to that image or that information you have in the image space, and you're interpolating between these two things. So if you take a reference image, noise, and back generated with null text, okay, so that's coming back to that, you're going to get this. This is pretty close to this. Slightly different, but it's pretty close. This is the generated image. But now you can start doing action. So now this says that this third line says that what we have has this property of that and reverse, and we can get back the universe. Okay. So in particular, there are you can think of there's a whole universe of structural causal models, different models. If I'm on one model, go back to noise and come back to that, then it is indeed coming back to that. Now I'll just finish this and then I'll take the question. Now I can start doing a do. I can do text conditioning because these models have a text field. If I now on the same noise sample that generated this, put in silver sculpture, this is what we get. If I put in tiger, this is what I get. And so that's what RF inversion is, a flow back and flow forward. And so it's computationally very, very cheap and can be built on, it can be actually implemented easily on sort of edge device. Yes. Flux. Flux, Flux is, so this is no control. This is the base control. This one. There is a base, not this one. There's a base field, which will let you, this is UT comes out of flux. You go back and you go forward. You may ask, if it's an ODE, why is it that when I go forward and go back, it doesn't work? There's discretization noise. The problem is there's really no backfield. How do you get a backfield? You run the forward, you take small enough steps, assume continuity. So assume the forward field and the backfield are the same at that point. Okay. And then if you're going this way, turn the sign and go that way. This is going to lead to small errors. It's enough for those errors to propagate and cause this. Agreed? If you take extremely fine steps, most likely you can get something much closer. But there's a second problem even if you do that. You can text conditioning will then throw it somewhere else. So I need to have this property that the abduction and your model are consistent with each other. You need to somehow ground on that image, which you know is where it's all starting. And they control the minimum. What we are doing by the coupling to the typical is actually putting a second field, which is pointing to that in the reverse direction.
Is there some prototype example such
So these are all these images are real, meaning it is running on actual flux. You can actually generate these images. You can play with this. It's an Hugging Face. There's a demo out there. And more than that, even internally within Google, this has been productionized in several pipelines, and it's working very well. I don't want to say anything more on sort of this mic. These are all anything here we just are real experiments, whatever I've shown here. So here are other examples of actually this pipeline in practice. So I give you this your scheme. So I can give this as a reference content. Flow back, give this caption, it comes back here. Flow back, give this caption, gives this, and so on. So it's a method for sort of editing these kinds of things. Okay, I'll just finish up then. So there's a second thing that that's very useful in the paper. I'll quickly talk about that. So these flow models are all ODEs. Sometimes you want a stochastic model instead of this flow model. Why you may wonder, why do I want a stochastic model? Because in some case, if you have a higher order solver, then these require actually stochastic solvers. There are people who have built a lot of pipelines for diffusion type models. And so you want to convert a flow model to a diffusion model so that you can put existing tools and build pipelines around that. Okay. So, and SDE samplers also robust to corruption. A flow model, initial condition will just stay all the time. A stochastic model has that robustness to corruption. Okay. So we can take whatever we did, these control flows, and actually get stochastic samplers, and the pipeline is well understood actually. You have any ODE if you has a density evolution given by the continuity equation. So you write the continuity equation for that, you get a way how this density evolves. Then you basically say, I want to construct a stochastic differential equation that has the same density evolution. That's the Fokker-Planck equation. These are all classic methods. So you can use a Fokker-Planck equation and then match things. So essentially and if you want to understand more about this, my tutorial on diffusions has a much deeper discussion of this. But you can go between flow models and stochastic models. And this is not our work, by the way. This is 1970s, 60s, 70s. I mean, this is all they're going between these things actually well understood in math literature. So really, if you have a flow model, you can get a stochastic model or vice versa, and you can learn all these coefficients. And you can do that indeed for this stuff. I have 2 minutes. I'll wrap up. I'll show you some. Let us see what kind of stuff we can do. Okay. If you take sort of this original image, use an SDE edit. So SDE edit is a stochastic system, and so it's not doing abduction. The noise, because you're adding noise, you're drifting away. And so there's a tension. If you flow it too back, you're losing all structure. If you flow it just a little bit back, you don't have enough control to actually edit it well. So this image you get with sort of SD edit like this. They think prompt also add glasses. This is what we are able to get with just flow back and flow forward. These methods are also very good, but these are training-based method. Okay, you need to do some more training on these kinds of things. So what we are able to do is sort of training free and optimization free, go back and forth. Let's see. Yeah, so I think I'll, since I'm almost out of time, you get a sense of what these methods can do. And so there's been a lot of interest from the community once we released RF-Inversion. In particular, somebody else took it and we put it into Mochi, a video thing. And you can now generate videos where you take a particular video and create videos in different styles. So once you have this pipeline of flow back and flow forward, you can do this for other types of editing things. So, and of course, within Google, there's a lot of applications for this and actually are being productionized. So at some point, you may be using these kinds of things. Okay, I'll stop at this point. Thank you.
Okay, I'll take one question.
Maybe.
So, understanding this is still the next step with reverse on the generation again. So is there any kind of like basement that wants to do single step reverse, single step whole?
No, it still takes tens of steps. I'll leave it at that. Yeah. Well, I'll tell you a way you could do that, but it's going to be impossible. I'll do 2 RF or something like that. Okay, if you can train a model which is 2 RF, then I can straighten it and do it in single step, right? But nobody has trained a 2 RF model.
Okay, let's thank Sanjay again.
Thank you.